Okay. The third speaker is Professor Yuguang Shi from the Peking University. The title is Non-Compact Manifolds with Positive Scalar Curvature. Let's welcome.
Yeah, it's my great pleasure to be here. I would like to take this opportunity to thank the organizer for giving me this choice. And also, I would like to say happy birthday to Professor Yao. Actually, the topic which I will talk is initiated by Professor Yao and Shen. Now, this is the outline of my talk. The main goal of my talk is to study the following things. Now, let M be an open manifold and kappa be an electric constant. We want to study under what kind of condition we would have infimum of scalar curvature G is less or equal than kappa. Here, G is any complete metric on M. I will study this problem in following two steps. Sorry. So in the first part, I will discuss certain non-compact manifold or open manifold admitting no complete positive scalar curvature metric. Also, I would like to prove that I would present certain complete. I would like to show that so no complete and uniform positive scalar metric on this manifold. Sorry. K is a given constant. No, infimum scalar curvature. No positive scalar curvature, so infimum scalar should be less than kappa. Yeah. Okay. Now, the second part, I will discuss various root type theorems on certain complete and non-compact manifold. That is, under certain conditions, geometric normalization conditions, the infimum of scalar curvature is less or equal than kappa. Actually, this talk is based on my joint work with my several group of people. Hao Tianze, who is my current PhD student, Shen Yukai is my current postdoctor, Wu Lenzhang is my current PhD student, Wang Jie is my friend, and Zhu Jingtian is also my former PhD student. Okay, let's get started from some basic facts of scalar curvatures. Now, by definition, scalar curvature is a trace of a Ricci tensor. Ricci tensor is a symmetric two tensor on a manifold. A nice way to understand the scalar curvature is the following formula. That is, let BRP be a small geodesic ball with radius R and center P, and we just look at the expansion on the volume on BRP. Now, this is the formula. And the capital RP denotes the scalar curvature at P. So by this formula, we know that the larger scalar curvature is, the smaller the volume would be. I'm always very curious at following the two facts. That is, all compact differential manifold with dimension at least 3 would admit a smooth metric of a negative scalar curvature. Actually, this is a simple corollary by a theorem of Professor Yao and Gao Ziyong. Now, the first thing is that not all manifold admits positive scalar curvature metric. Actually, this is a classical result due to Lishinovich. I think he proved it about 60 years ago. And since then, the question to study under what kind of manifold admits or cannot admit positive scalar curvature metric become one of central problems in Riemann geometry and topologies. Okay, now let's look at some typical example of scalar which admit scalar curvatures. Now, the first theorem is due to Professor Yao and Shen's, which is a solution of Garo conjecture. That is, take a torus, dimension is between 3 to 10. So torus admits no positive scalar curvature metric. Here's a distraction of dimension due to the regularity of area minimizing height surface. And in 1983, Gromov and Lawson proved the following result that all compact Cartan-Andermann manifold admit no positive scalar curvature metric. Here, Cartan-Andermann manifold means manifold always admit a non-positive section curvature. Non-positive section curvatures. And in 1998, the loop proved the following interesting theorems. That is, let Sn be a standard unit sphere, and G is another metric on this unit sphere, which is bigger or equal than G naught. And if the scalar curvature of the G is at least bigger than the standard ones, then G must be isometric to G naught. Okay? Now, here's my understanding behind these typical examples. The first one is that non-existence of positive scalar curvature metric really depends heavily on the topology of the underlying manifold. Roughly speaking, a compact manifold admit no positive scalar curvature metric usually would have complicated topology. For instance, in two-dimensional case, its genus should be bigger or equal than 1. The third one is the following, that one cannot enlarge the metric in all directions and increase the scalar curvature simultaneously. More precisely is the following observation due to Gromov. Let Ng be compact manifold, and Ng not be a compact manifold with constant section curvatures, which denote kappa, and F is from N to N, which is 1 Lipschitz and non-zero degrees. Then the infimum of scalar curvature cannot be bigger or equal than these ones. Here, Cn is a constant, depends on N, which can be written in explicitly. And this one is injective radius of universal covering space of this manifold. Now, let's look at the previous two examples from the perspective of Gromov's observations. So now this is a standard unit sphere, and G is another metric which is bigger or equal than G naught. So identity map is of course 1 Lipschitz and degree 1. Then, according to the observation of Gromov, the infimum scalar curvature of G cannot be bigger than these ones. But in this case, we can calculate this in very explicitly way, that it's just the scalar curvature of the standard unit spheres. Okay, so this is the Leroux theorems. Now, this is our second example. That is, let Ng be Cartan-Andermann manifold, a compact Cartan-Andermann manifold, and M be any manifold, so that there's a map F from M to N with non-zero degree mapping. We will say that M dominates N in this case. Then M admits no positive scalar curvature metric. Suppose not. Then there's a metric G on N, and which is a positive scalar curvature metric. And we can choose a constant lambda large enough so that F is 1 Lipschitz, because M and N is compact. So there is always such constant. And actually, note that this is Cartan-Andermann. The targeting manifold is Cartan-Andermann. So its injective radius of its universal covering must be infinities. And then by observation of Gromov, we get infimum scalar curvature cannot be bigger than 0. That means such manifold admits no positive scalar curvature metric. Okay? So this is for compact case. Oh, sorry. The third manifold which admits no positive scalar curvature metric is so-called SYS manifold. Now here's definitions. Let M be a compact manifold, and beta 1, beta n minus 2 is in first cohomologic class. And this is a fundamental class of M, and we do the cap product with those first cohomologic class, and which is the element of sector homology class. And we assume this element is not contained in the Horace map. So we say such M is SYS. Now here is an example. The torus, standard torus, and sigma here is a compact surface with genus 1 product with n minus torus is all SYS manifold. Okay. Now we have the following theorems. Let M be compact SYS manifold and dimension between 3 and 10, then M admits no positive scalar curvature matrix. Okay, this is for compact case. So how about non-compact case? Now, non-compact is quite complicated. Now let's begin with several simple example. The first example is that a torus cross a product with a line admits no complete positive scalar curvature metric. Actually, this we can prove it by width estimate. But if we pick up, if we product with R2, then this manifold, such a manifold would admit a complete positive scalar curvature metric, but admits no complete and uniformly positive scalar curvature metric. Now, let me show you why this manifold admits positive scalar curvature metric. Actually, there is a rotationally parabolic metric on R2, which can be written very explicitly. And those scalar curvature of a parabolic metric is positive. Actually, curvature operator is positive. This is a convex surface in R3, actually. So we just do the linear product with torus and get a complete positive scalar curvature metric on this. Okay? And the third example is that if a torus product with R3, product R3, that would always admit a complete and uniform positive scalar curvature metric. Now, let me show you how to construct it. Let's take a half cylinder like this, and this is a hemisphere, and we just gluing them around the equator, and we will get it like this. And then we just make it smooth and get this is R3, topologically R3, and we get a complete and uniform positive scalar curvature metric. And then we just do linear product with torus. So we construct a complete and uniform positive scalar curvature metric on such a manifold. I should say that all above manifold are Cartan-Andermann manifold, but some of them admits no positive scalar curvature metric, and some of them admits a complete uniform positive scalar curvature metric. Okay, so that means the non-compact case, it is quite complicated. Now here another known result. The first one due to Gromov-Flosson, that Tk be a linear subtorus of Tn, and then we just remove Tn by Tk, and the remaining part admits no complete positive scalar curvature metric. Oops, sorry. Yes, about 4 years ago, Leshu, Engel, and Professor Yao, and independently by Cholosh and Li Chao, proved the following result: that they proved that the connected sum of torus with any manifold, either compact or non-compact, would admit no complete positive scalar curvature metric. And later, Xu Li Chen generalized this result. She proved that any compact SYS manifold connected sum with an arbitrary manifold, either compact or non-compact, also admits no complete positive scalar curvature metric. Recently, Xu Li Chen, Jianchun Chu, and Zhu Jingtian proved the following things. They show that any compact connected sum with compact spherical manifold with arbitrary manifold would admit no completely positive scalar curvature metric. Okay, but the dimension should be between 3, 4, 5. Okay, and Gromov proposed the following conjecture in his 4 lecture notes on scalar curvature. He said that if a compact oriented manifold X0 cannot be dominated by a compact manifold with positive scalar curvature, then it cannot be dominated by a complete manifold with positive scalar curvature. Now, let me explain some terminology for you. Let X be a compact manifold. We say X dominates X0 if there is a map F from X to X0 with non-zero degrees. No, so this is for compact case. And if X is open manifold, we say an open manifold dominates X0 if there is a map from X to X0, and outside a compact set, F is constant. So in this case, we can still define degree for those F, and we require that degree is not equal to 0. In this case, we also say that an open manifold dominates a compact manifold. Now, here's some remark of dominations. Usually, if a compact manifold X can be dominated, X0 can be dominated by X, and usually the topology of X is much more complicated than that of X0. And also this is true for non-compact case. So with those things in mind, it seems natural to believe that the answer to the following to the following special case of Gromov conjecture should be affirmative. So that is, if X naught is compact SYS manifold, you can image it is a torus, and X is an open manifold, and if K is compact set of X, and we assume F is constant outside K, and the degree equal to 1, then X admits no completely positive scalar curvature metric. If this is true, then we can recover the above mentioned results, because all those results are considered connected sum, and we always can find a degree 1 map from X naught connected M to X naught. Sorry. And now the second remark is that let this be a first cohomologic class as defined as a definition in SYS manifold. Without loss of generality, we can always assume those first cohomologic class, you can image just one forms, are linear dependent around P, because the first base number of the sphere is 0. So we can always assume it is linear dependent around the P. Now this is our result. Let M be compact SYS manifold. Sorry, we should assume dimensions between 3 and 7. Now I make a mistake here. This should be 7. And gamma be a compact submanifold of N, and M the open manifold. We assume that M is F is from M to N be a continuous map, so that either it is proper or F maps to outside max the domain outside K, outside K is to this gamma for some compact K, and we assume degree is always equal to 1. Then, if gamma is the first base number of gamma not bigger than M minus 3, then M admits no completely positive scalar curvature metric. And if gamma is spherical and the codimension big at least 3, then M admits no complete uniform positive scalar curvature metric. Okay, this is our result, which is proved by just. Now here's some remark. The same conclusion is true if those first cohomologic class is linear dependent on gamma. If we take gamma as a point of N, then above theorem give an affirmative answer to the special case of Gromov conjecture. Now, the second remark is that more generally, we can define the notion so-called SYS, open SYS manifold. And we can show those open SYS manifold carries no complete positive scalar curvature metric with dimension between the 3 and 7. This should be 7. Now, if N is a closed SYS manifold, then N cross R is an open SYS manifold in our sense. The main argument is to use the minimal surface techniques together with careful topological analysis. Okay. Now, this is for non-existence of positive scalar curvature. Now, let's move to this part that we want to prove a certain manifold admits no uniform positive scalar curvature metric. Now, let's begin with a Gromov conjecture. Let X be a N manifold such that X minus points admits no complete metric with positive scalar curvature. So the manifold looks like this. This is X minus point, and let V be obtained by removing a small open ball. Now this is V here, and assumes that let G be a metric on V. V is a compact manifold with a boundary, non-empty boundary, which is scalar curvature on the V is bigger than sigma, which is a positive constant. And if the low neighborhood of this boundary is homomorphic to cylinder, then low cannot be bigger than this constant. This is not optimal, I should say that. Actually, this is kind of width estimate. This is a conjecture made by Gromov. And he also pointed out that if X is SYS manifold, and this can be done by Shen-Yao's dimension reduction argument. Now, the following picture illustrates the main argument to prove this case. Now, let me show you how to do that. Now, let beta be in the definition of SYS manifold, because the first Betti, as I said before, that the first Betti number of the sphere is equal to 0. So beta, we can show that beta restriction to this sphere is equal to 0. And then we can do the covering space and take a band from this covering space looks like this. Because beta equal to 0, so the covering space, this is component of the V's, and each of them are compacted. Then we can use the mu bubble argument. Here is mu bubbles. And if rho bigger than this, rho is bigger than this, then we can show there exists a mu bubble here. The mu bubble is always carries a positive scalar curvature matrix. However, it is SYS, so it cannot carry it. So these are contradictions. The contradiction means rho cannot be bigger than this. Now, this is our result. Let M be a compact SYS manifold, and the dimension is between the 3 and the 7. And gamma is compact submanifold, and the codimension at least 3. We assume gamma is spherical. That is, the Horace map is always surjective. And if scalar curvature is bigger than sigma, and then any two neighborhood U1 and U2 of gamma should be, the distance between any two neighborhood of gamma cannot be bigger than these ones. This is also kind of with estimate, especially M. If we remove gamma from M, then the main part does not admit a complete uniform positive scalar curvature matrix. So if gamma equal to 0, then if gamma is a point, then this is automatically spherical. But in our case, the beta restriction on gamma may not equal to 0, so should be much more complicated. That is more careful analysis needed in the proofs. But I think I have no time to talk about the proof. Okay, this is for the first part. Now here's the summary. That is, we can define a kind of notion so-called open SYS manifold. And those manifold admits no positive scalar curvature matrix. Now, here is some example of our open SYS manifold. M is closed SYS, is a standard closed SYS manifold. And M times R or M minus gamma, which gamma is a submanifold with Betti number not so big. And those compact open manifold, sorry. And those open manifold is also open SYS. Okay. Now, this is the first part of my talk. The second part is on the Lu-type theorem. And the main goal of this part is to understand under what kind of geometric normalization on G, so that the infimum scalar curvature of G cannot be bigger than kappa. Here, kappa is a positive constant. Now, let's begin with some simple example. This is the standard two spheres, and G is another metric, and G is bigger or equal than to G naught, and the scalar curvature of G is bigger than 2, then it must be isometric. Actually, this is derived from the Gauss-Bonnet formula, because the integral of scalar, in two-dimensional case, the integral of scalar curvature is equal to 8 pi. And then we can, by these conditions, we know that G must isometric to G naught. But for the high dimension case, it's quite complicated. Now, this is the root theorems which I mentioned a couple of minutes ago. And here are some remarks. In this case, the identity map is always one Lipschitz and with degree, which serves to be a geometric normalization. I would say this is kind of geometric normalization. And the second remark is that actually the standard sphere can be replaced by any strict convex type surface in Rn. That is, if you take a strict convex surface replaced here, and a similar theorem is still true. The root theorems was proved by Dirac operate originally. But in some low dimensional case, it can be handled by mu bubble arguments. And one Lipschitz condition can be relaxed to area non-increasing. Now, so how about the other model space? Now, we are interested in a model space like this, Sk times n. Here, n is enlargeable. For instance, torus or Euclidean space. Now, the observation is here that for those enlargeable manifold, you cannot admit, does not contribution to the scalar curvature of the whole manifold. So there must be certain restriction on these factors. Now, here is a formulation of our problems. Now, let Mg be a compact orientable Riemannian manifold with scalar curvature bigger or equal than this one, which is a scalar curvature of the SKs. We assume that there's non-zero degrees and one Lipschitz map from M to this. This is kind of geometric normalizations. Then we want to show that Mg is locally isometric to this, to the model space. And also we also want to prove a similar result for this one as model space. This is non-compact case. Okay. If the answer to above problem are affirmative, then there would be no non-zero degree map provided scalar curvature bigger than this case, strictly bigger than this one. It seems there are three types of model space we should consider. The first one is compact case, that Sm. And the second one is Sm minus 1 times R. The third one is that Sk product with n high dimension Euclidean space. And actually, there's a result due to Zhang Weiping. He proved that let Mg be non-compact manifold and non-compact and complete spin manifold. He should assume the manifold is spin. And F is from M to Sn. And F is constant outside is a compact set, and degree not equal to 0. And this area non-increasing. Then he can show that the increment scalar curvature is not bigger than zeros. An interesting application is that under spin assumptions, let Mg be a non-compact and complete spin manifold with scalar curvature bigger than this. Then there is no manifold, no map from M to Sn, so that it is constant outside K and degree non-zero, the area non-increases. So now, see, here is a problem. Is it possible to show that the same result without spin assumptions? The one difficulty is that for high dimensional case, if manifold is not spin, then you cannot use Dirac operator or Gauss-Bonnet formula directly. Recently, we proved the following result. Let Mg be n-dimensional compact orientable Riemannian manifold. A scalar curvature is bigger or equal than 6, and the dimension of n is between 4 and 10. If there is a non-zero degree and one Lipschitz map from M to this model space, then the manifold M must be locally isometric to the model space. Okay. Now, so the second problem is that if it's possible to prove the similar things in non-compact case, that is, use this S3 times Euclidean space as a model space. Unfortunately, the answer is negatives. And now here is main observation, because the root type theorems are not true on the Euclidean space for high dimensional case. Now, this is a counterexample to the root theorems. Let sigma n be a parabolic of revolutions in Rn minus n plus 1, which is a graph of on Rn. And P is just denoted projections. So P is one Lipschitz and non-zero degrees and propers. And whilst the scalar curvature of sigma is strictly bigger than this constant. That means the root theorem on Rn is not true. So that means we need some extra conditions. Now here's observation. By this estimate, one can show that there's no, there is no proper and one-Lipschitz map from Euclid's from this manifold to standard Euclid space. If we assume scalar curvature is bigger than a uniform positive, that is always bigger than a given delta, given any deltas. Now, by a similar argument, and together with our theorem, which proved just now, we can show that for any delta positives, that M is from between the dimension between the 5 and the 7. Be a non-compact orientable manifold with scalar curvature is bigger or equal than 6 plus delta. Delta is any positive constant. Then there is no prop and one Lipschitz map from M to this model space with non-zero degrees. This cannot be removed. Okay. Now, the next observation is actually a simple conclusion of positive mass theorems. That is, any compact perturbation of Euclid space with non-negative scalar curvature must be trivial. And we proved a similar result on this. That is, one cannot do compact perturbation on this model space to get a manifold so that scalar curvature is at least 6, and there is a map F from M to this, and being proper and one Lipschitz and non-zero degrees. Just something like a positive mass theorems. However, it is very interesting to see that the saturation are completely different from, very different from this if we take this as model space. Now, this is our theorems. This is before manifold, four-dimensional manifold with non-compact and orientable. And the scalar curvature is bigger or equal than 6, and this is a map from M to this S3 products with R, and it is prop and one Lipschitz with non-zero degree. If this manifold is geometric bounded, that is, the supplement of curvature operator is bounded and the injective radius is positive, then F must be isometric. This is kind of rigidity theorems. We believe this is not necessary. The geometric boundedness is not necessary, but we don't know how to prove it without such conditions. And we also show the following result. Let M be a non-compact, orientable, and a complete Riemannian manifold with scalar curvature strict bigger than 6. Then there is no proper and one Lipschitz map from M to this model space with non-zero degrees. Okay, this is our main result. Actually, I will skip this. Actually, I have showed the final conclusion of our theorem is that for any delta positives and M is between 1 and 4, the delta gap length extremity of standard sphere, three-dimensional standard sphere, is stable under Riemannian product. Actually, this is a question raised by Gromov. Yeah, I think I should stop here. Thank you.
Okay. Any questions? Minimal service argument.
Yeah, I don't know how to handle the singularity.
Okay, if there are no other questions, okay, let's thank speaker again.